Hello and welcome to episode 8 of Naturally Curious. My name is Clayton Law and today I'm joined by Wesley Burr. Wesley Burr is a statistician and a math professor here at Trent. How are you today, Wesley?
I'm doing well. It's a Friday. Fridays are good.
Yeah. Let's just jump straight into it. As a child, were you good at math or did it come natural for you?
Yes, very much so.
What other subjects like languages and sciences, were you good at it?
Yeah, I was good at almost anything academic. Academia is where I found my success, and good at almost all courses and all subjects of interest when I was a kid, at least.
So it can be just me, but before university, all I know about statistics is mean, medium, mode. That's basically everything I know about statistics. How did you get into statistics? Was it before university?
No, not at all. I didn't take any courses in statistics proper until my fourth year of undergrad. Historically, statistics as a topic of study was a graduate degree only. It's only in the last 40 or 50 years that you could even really study statistics as a profession at the undergraduate level. And so historically, it was always a master's degree, typically done after an undergraduate study in either mathematics or an area of hard science.
So what did you do before you decided to do statistics?
My undergrad degree is in engineering. I'm an engineer, and my degree was in mathematics and engineering with a specialization in communication theory, and I sort of drifted into statistics. My master's is in applied math, and then my PhD was in statistics, applied statistics, in areas that sort of crossed over all three of those disciplines, because really at the end of the day, I work on time series, and time series are an aspect of signal processing, and signal processing is what I studied as an undergrad. So it all does connect. It's just I went from engineering to math to stats across my lengthy education.
Correct me if I'm wrong. You did your undergraduate, your master's, and your PhD in Queens, and you received a postdoc fellowship there as well. Why didn't you just stay there? And did you not get an offer? Why did you come to Trent?
The postdoctoral fellowship wasn't a real fellowship. It was I finished my PhD in October. I had a fellowship lined up at Health Canada, where I was an NSERC Canadian Government Labs fellow visiting Health Canada, but it didn't start until the rollover of the next fiscal year. So my starting date was May something. And so I had 5 months or 6 months between the time when I handed in my thesis and finished my defense and was able to start my postdoc. So Queens, the department that I was attached to there, simply hired me to teach a course. So I was there as a nominal postdoctoral fellow. That was my rank, but the only funding I was really receiving was via the department for teaching. And so it was just a stopgap measure. It lasted for a few months, and then I moved on to my actual postdoc where I did my research. And it was just to pay the bills, make sure I had rent money.
And to fill in the gap between October to May. So
as much as I would have loved to have taken 6 months off, that's not the reality. Rent still needs to be paid, food still needs to be purchased, and you got to keep yourself busy. And I enjoy teaching, so I taught a course for the department and then packed up my life and moved to Ottawa.
Obviously, you didn't get to teach while you were in postdoc doing research because that's not an education institution, right?
That's correct, yeah. I wasn't doing a postdoc at or attached to a university. I was in the Population Studies Division at Health Canada, and so I was just, for 2.5 years, I was just working on an extensive project, which unfortunately didn't go the way we'd hoped, but we did get one paper out of it in the end, where we were studying the impacts and the effects of the closure of a oil refinery in Oakville.
So were you always thinking to be go into teaching, like being a professor or something?
I'm not really sure. I mean, when you're young, especially in high school or early university, you don't even really know what a professor does. You don't have any real context to understand the job or the role. Certainly, I liked learning, and I enjoyed being part of school. That was always something I enjoyed. And so I think in the back of my mind, I always sort of knew I was going to do graduate school, that an undergrad wasn't enough. But in what and for what, that was never clear. And it was only once I started graduate school and started to learn a little more about the system that I realized that actually this was something I wanted to do. And I've always been interested in teaching, and I've always been attached to it in some way. I started acting as a tutorial leader and workshop leader for the engineering program at Queens in my second year of undergrad. And so I was a tutor for those programs for 3 years. So when I started my master's degree at the same institution, they knew me already, and I was quite quickly moved from just being a tutorial leader to actually being given my own classroom and my own instruction and teaching sections of larger courses. So in my second year of my master's, I taught 2 classes.
So you kind of knew you wanted to do teaching since around second year university, around that?
I don't know that I wanted to be a teacher. I just knew that I liked the university environment. I liked what it seemed like people did. I really didn't have the context to understand what they did, but it seemed appealing to me. It sounds silly, but a part of my reasoning at the time was I saw a lot of colleagues or people who graduated with engineering degrees, and the thing about an engineering degree is, on the whole, most engineers go management very quickly. The actual life cycle of a practicing engineer who's actually doing engineering and hands-on work is somewhere between 5 and 11 years. And then you move up, and the only way to move up is to become a manager and to manage teams of engineers. And at some point, very quickly within that framework, you become more interested in the business side of things than the engineering side of things, and more interested in wearing a suit and working in an office and so on. And that did not appeal to me at all. I was not interested in that, and I don't like wearing suits. I find them uncomfortable, and I just generally wanted a job where I could be comfortable and also where I could be intellectually stimulated. And there's something to be said for the independence of academia. Yes, we have a fairly lengthy list of constraints on our time relative to our standards, but relative to the rest of the world, we have a wealth of freedom. We have tremendous amounts of freedom to choose what we want to research, to choose who we want to supervise, to choose even, to some extent, what we want to teach, how we want to teach it. And that freedom is appealing and allows you to be independent, and that's very freeing at times. As much as we say that, the university is still very structured. And, I cannot simply decide tomorrow that next year, rather than teaching statistics, I would like to teach basket weaving because I'm very interested in baskets and weaving. It doesn't work that way. And so there is still constraints on our time. Obviously, there is still requirements on our job that we have to do, but we still get a tremendous amount of freedom relative to the rest of the white-collar world. And that's quite appealing. And so once I got into graduate school, I knew this was what I wanted to do, and I won the lottery, and I get to do it. And that's unusual, actually. The ratio of PhDs granted in Canada to new hires in research or even teaching-oriented tertiary education is quite abysmal.
Yeah, I've heard something like every PhD student wants to teach, or wants to stay in academia, but their supervisor's still alive, so can't do that until they're dead.
It's not true that every. The ratio in statistics is nowhere near that. Something like half of all PhD statisticians immediately exit the academic world. Not even just doing a postdoc, but literally as soon as they're done their doctorate, they're gone. And they move on because there is a large amount of industry demand and government demand for statisticians. And so there are open hire recs, especially with the blow up of data science, in large numbers of companies that cannot be filled. And so if you have a PhD in statistics, you're extremely desirable. And if you want a job, you have one. You may not have the job you want, but you have a job, and that job will pay a reasonable middle class plus lifestyle. So in that sense, there's a very large sink, sinks and sources, which takes this supply of PhD statisticians and sucks them out of the academic world quite quickly. And you can see that when you look at the general job market. There may be approximately the same number of positions available this next year in statistics departments or mathematics and statistics departments for statisticians as there are for mathematics departments hiring mathematicians. The ratio is not too far off from 1 to 1, and yet the supply of people interested in these statistics positions is an order of magnitude smaller than the supply of people with PhDs in mathematics looking for mathematics positions. And it's even worse in the experimental sciences because there's more money in the experimental sciences, so in physics and chemistry and biology and environmental science, which means the labs are larger and the number of graduate students is larger and the number of PhDs granted is larger. And yet there's no more positions in that field than there is in, say, mathematics. So in that sense, statistics is a great profession to go into because If you want to be an academic, the competition is less steep, and if you don't, they'll pay you scads of money. And that's kind of appealing.
While we're talking about PhDs and masters, I've heard a lot of people saying, like, if you're thinking doing PhD or just going straight to work, going to work is great as well because you get that extra 5 years of experience, and the PhD in economics is not super duper much better than a master in economics. It doesn't seem like this in statistics.
It's not true in statistics.
Why is that the case?
There's a very large difference in the seniority and the abilities of someone with a master's degree versus a PhD in statistics. And the same is true in economics, but I mean, you mentioned economics, so it's all about incentives. It's all about what people are willing to pay you to do. And at the end of the day, someone with a master's in economics is capable of doing a lot of the jobs that people in business are willing to pay for. Whereas a PhD in economics may be so hyper-specialized that what they do is only appealing to a few sources, and therefore there is not much demand and there's too much supply. Whereas in statistics, if you do a PhD in any form of applied statistics, you have a tremendous breadth of skill. You're not narrow at all. Theoretical statistics, you can still be very, very narrow in your area, but applied statistics, you tend to be very, very broad, which means you are appealing to many, many people. And that means there's a lot of demand. A lot of people are interested in hiring said people, and that increases the demand, and you do come out ahead. Now, having said that, you still don't come out far enough ahead to compensate for the fact that you have lost the opportunity cost of 5 or more years. That's the reality. There are very, very few graduate degrees that actually pay off in the long run.
Really?
From a purely economic point of view.
Okay.
But it's not about the money. I mean, it's about the money, but it's not all about the money.
It's not always about the money.
At the end of the day, a PhD in a science, a hard science, will definitely get paid more than a master's degree in a hard science year to year. So that is good. And why won't most people do it? The work is more appealing. The seniority is better. The freedom, the independence, the responsibilities are more better. You may get to work on more interesting problems. And at the end of the day, if you do a PhD, it's because you are naturally curious and you are passionate about something. If you manage to slog your way through a PhD without being passionate about it, I genuinely feel sorry for you. It's a very long slog. It's unpleasant at times. It's a tremendous amount of work. If you don't find it intellectually stimulating, then what are you doing?
Get out.
You certainly aren't getting the economic benefits. It's not like an MD or an LLD, where it's that degree is the bar that you must pass, no pun intended, to allow you to then obtain the career that goes along with it. You cannot be a lawyer without passing the bar and having a law degree. You cannot be a doctor without having a medical degree and passing your boards. And similarly, so if you want to be a doctor, that's the path you take. You don't have a choice. If you just want to work on interesting problems or you just want to make money, a PhD is a waste of time. You can do that without that, and then you save 4 to 6 years of earning potential at the very start of your career. And that's the part that people are like, well, it's just 4 or 6 years. Like, yeah, it is. But it's the first 4 to 6 years. And so those first 4 to 6 years are actually arguably the most important years because you're starting to build wealth and everything cascades from there. So if I had left school in 2005, when I graduated with my honors degree in engineering, I would have started, the average starting salary for people working in the sort of field I would have gone into was around $60,000 a year at the time. So that's a middle class income. And I would have started there. And by the time I finished my postdoc, I would have had 11 yeyears of salary growth and salary earnings and almost no student loans. And they would have been paid off almost instantly. I would have owned my house, and I would have been very well established at the same age that I walked out of grad school and a postdoc with almost no assets, significantly more debt, and 11 years of my life gone. Right? And that's the reality, is you don't do it for the money. You can't do it for the money. If you do, you're an idiot. You don't know how to do basic economics. You do it because it's the job you want to do, or you do it because you're passionate about it, or you do it because at the end of the day, money doesn't matter that much to you. Money's necessary. It buys us things. We can't have nice computers and fancy microphones and cars without money. But how much do you actually need to be happy? And finding a job that fulfills you and makes you happy is more important than how much money you get paid. You only get one life. Live it in a way that actually brings you some level of joy.
Yeah, I guess if you start working with your undergrad degrees in engineering, by now you'll be doing work in an office and wearing suits.
Oh, I would, yeah. Absolutely.
That sounds fun for you.
No. But I would also be paid, I mean, given the typical career trajectory of people who were in my class who actually went that route, I'd be a manager or a senior manager by now, and I'd be paid somewhere in the 120 to 150 range, assuming I hadn't navigated from the engineering world into the data science world, in which case you can double that number. And I'd be probably wearing a suit, and I'd be managing people, and I'd be working 9 to 5, and my evenings would be my own, and I would have more financial wealth and significantly less joy. I wouldn't be teaching, and I enjoy teaching.
Earlier you have said that statistics is like you don't really get to study statistics until you're graduate.
No, historically,
like 50 years ago.
Yeah, so I was actually talking about this with a colleague this morning, and you do get to study statistics at the undergraduate level now. Absolutely. There are a number of very, very good undergraduate programs where your bachelor's degree is in statistics. Unfortunately, the majority of what you were exposed to at that level is still idealized. It's simplified, and it's idealized, and it doesn't actually get at all of the beauty and depth of what is possible with statistics, and that is reserved for graduate school. But the same is true of mathematics, the same is true of physics. On some level, our professions are mature enough that there is a depth to them that is not possible to teach in only 4 years, except to the most exceptional students. And we aren't aiming at the most exceptional students, we're aiming at students in general. So there's a course at Harvard. So if you go to Harvard and you major in mathematics, there is a course at Harvard in the first year of undergrad. So just to take yourself, imagine yourself as a recent high school grad. You're bright, you work hard, you're prepared for this. You go to Harvard, and in your first 8 months, you do the entire undergraduate curriculum at another university. It's a course that runs 1 year and covers an entire undergraduate curriculum. Just really fast.
That sounds really intense.
It's extremely intense. They have something like a 50% dropout rate by the second week. Very few people finish it. But if you finish it, you're effectively done your undergraduate degree in terms of material at the end of your first year. And then from there, you spend your second year, third year, fourth year studying whatever you feel like. And in essence, you're a graduate student without being a graduate student. So when you finish a degree like that, you're already well into PhD level material. And so all you have to do is add the research on top of it and learn to be independent and not just learn, and you're ready to go. So it's possible, but again, only the most exceptional of the most exceptional can be done that way. So yes, I could take an undergraduate, a sufficiently motivated, sufficiently bright undergraduate, and I could teach them up to the end of a master's in 2 years. The work would be brutal, and they would have to be entirely engaged and extremely bright and extremely self-motivated. It could be done, but we don't, because that's not how we teach. We teach to an average. The average is different levels at different institutions, but on the whole, we're aiming to bring everyone up to a certain level, not take 1 or 2 exceptional students and polish them to an incredible shine.
Statistics is an entire field on its own, rather than like a subfield under math.
No, it is not a subfield on math.
Why do you think it deserves its own field? Maybe I'm wrong, but I can say linear algebra and topology are just as deep as statistics. Why don't they deserve their own field, but they have to be a subfield under math? And why do you think statistics deserve its own field?
Why do you think physics deserves its own field? Why do you think computer science deserves its own field? They're just sub-areas of math.
So it's like enough people think that it deserves to be its own thing.
No, it's not that. It's that the problems that you're interested in are different. I mean, there are a large number of mathematical sciences. Physics is a mathematical science. Chemistry, at least not empirical, but theoretical chemistry is largely a mathematical science. You used like a large amount of mathematics in there. So is computer science. There's lots of people in computer science who actually do a tremendous amount of mathematics. Our current chair is one of them. Dr. Feng does functional analysis. She also works on big data problems and computer science problems, but she works on functional analysis. It's applied mathematics. She does some very high-level differential equation work. Okay, but she's a computer scientist by training, officially. So the point is, there are fields, statistics, computer science, and physics being the three sort of primary ones, who are mathematical sciences. They use mathematics at its very deepest level as a tool for solving problems in their area. But they're not math. And mathematicians aren't really interested in their problems, on the whole. And mathematicians don't want to own them. And mathematicians do different things to them in terms of what they're interested in and what a mathematician would want to do with their time. A lot of the problems that we look at, they're just genuinely not interested in them. So statistics is a mathematical science. I would never deny that. But it's not a sub-area of mathematics any more than physics is. It stands on its own. The problems we're interested in are different. And the way we approach our problem solving is different. And the fact that we are fundamentally a science is different. Mathematics isn't really a science. It's closer to philosophy than it is to science. It's axiomatic. There's areas of mathematics that are not defended by reality. They're not driven by empirical data. They are beautiful and pure and philosophical. And we have entire areas of mathematics that are built upon foundations that are abstract. And more mathematics is abstraction layered on top of abstraction, because the abstraction gives you ways of looking at problems that are more general than just solving a problem. Mathematicians aren't terribly interested in solving individual problems. They're interested in classes of problems. And statisticians do the same thing, but we're primarily interested in classes of data. At the end of the day, if you are a statistician, you work with data. You work with observational data about the reality we live in, and your goal is fundamentally the quantification of uncertainty. We are determining how to handle stochastic aspects of experiments, of designs, of sampling, of analysis of data, of probabilistic distributions, of queuing theory, of time series. We're dealing with the fact that we observe things in nature that come with a stochastic component, a random component. How do you deal with it? That's what statistics is all about.
So many fields uses statistics. Physics, like psychology, sociology, political science, economics, they all use quite a bit of statistics. So it sounds like no studies can be done without statistics.
Not studies that you're interested in actually inferring conclusions about.
But statistics really only existed since the 19th century.
Yes.
How did they do studies before that?
They stamp collected. So, before the invention of modern statistics, which is a little more than the 1900s, there was aspects of it as early as the 1820s and 1840s for sure. But before that, everything was either empirical or it was stamp collecting. So you know what stamp collecting is. It's a hobby. People collect stamps. You can collect stamps because every year the postal services of the various major countries release new stamps with new pictures on them. And so you collect them because they're pretty. My grandfather did it. So when I was a kid, I used to collect stamps. And you can collect all kinds of stamps, and they have different pictures on them, and some of them are worth a lot of money. But it's stamp collecting. You find something that's pretty, you take it, and you put it in your book. So take biology, before it was called biology. Go back to the time of Origin of the Species, or before. What did you do if you were a naturalist? You observed the world. You made observations about the world around you, and from those you tried to infer logical conclusions. You mostly didn't work with very much data, because there was no way to really analyze it, because mathematics was still in somewhat of an infancy. You gotta remember, the calculus was invented in the 1600s. And from there, we started building mathematical models. And then, from there, we were able to do things. But as recently as the 1800s, astronomy was still working with models that were fundamentally flawed. And actually, you can look back, and regression, the concept of regression, was invented in the 1800s. and came out of some methodologies that had been developed for astronomy, where you had a series of observations on subsequent nights, possibly with missing nights because of cloud cover where your telescope didn't observe it, and you were trying to infer things about orbital paths, or about the distance to other planets, or things that are fundamental astronomical constants. And they invented a methodology that is essentially in prototype was regression, the idea of trying to infer things from data and minimizing the square of the error. But they didn't really understand what error was stochastically, because probability was still in its infancy and was only being developed from a gambling thing to something that was a more general theory. And it actually took until well into the 1800s before probability was refounded on a robust mathematical framework, because there's a fundamental transition which occurs when you go from probability in the discrete case, which is quite simple, dice, flipping coins, dealing with gambling problems, to a continuous case, and you have to redevelop the entire concept inside of Borel sigma algebra as a measure. Otherwise, there are pathological examples that break probability. So once you had foundations there that worked, things started to move quite quickly. And by the 1940s and 1950s, we had stochastic processes, and they were well developed and well understood and were rigorous theoretical objects. And we had some aspects that had come out of the empirical world, pulled from oceanography, pulled from astronomy, pulled from other areas of physics to bring those time series. And in the 1920s, Fisher essentially single-handedly launched the sub-area of statistics known as experimental design, which is how do you design an experiment such that the results of that experiment can be generalized to populations in a way that is causal. So we can actually infer things about our world in a causal relationship. And that was a big step.
So when statistics came along, did it destroy a bunch of old theory that once thought to be correct, but then, we got data. You're wrong after all.
Oh yeah, of course. Science is a very, very slow self-correcting process. And so it's why it amuses me to no end when you see politicians, particularly right-wing politicians, convinced that there is an academic conspiracy to promote climate change. And it's like, if there was actually a conspiracy, one member of that conspiracy would throw everybody else under the bus so fast it would make your head spin for the prestige of shutting them down. Science is all about correcting and coming up with clever things. We are naturally drawn to trying to find answers to things that show that old theory is wrong. And if it's wrong, we correct it. Unfortunately, it's a slow process. It's not an instantaneous thing. But nonetheless, it's sort of silly. And so, yeah, of course, once we had statistics, they started to be able to demonstrate certain things didn't behave the way that we thought that they did. And we've done some examples in our class, and I tend to try and bring these historical examples in, like the violation of the normality assumption and how the t-distribution was invented, and just in general, a series of things that led to modern statistics.
So I know you're not the biggest fan when it comes to some people how they interpret confidence interval and p-value, because they go it's in the range, so it's good, or it's not, then it's not good. You gotta have a line, right? Do you have a solution that you can propose? We have to have a cut-off point.
You don't. Why do you need a dichotomization? What's it for?
We don't need it?
No. This is the problem. Statistics, by its very nature, is not actually predisposed to providing you with dichotomizations. Dichotomizations are not valid. There's not really in nature a lot of true dichotomies. True on-offs, yes-nos. You have, take genetics, for example. It's quite remarkable what the level of viability of crossbreeding actually can be. And I'm sure you've heard of ligers, and you can actually, and even just sort of donkeys in general, and the idea of a mule, is you can crossbreed species and actually get a viable young that is able to be birthed and live and breathe and think and exist, but where you've done so much that you've effectively broken the genetic train, and those are no longer fertile. They cannot have offspring again, right? And so they're dead ends genetically. And really, at the end of the day, there's not a lot of true dichotomies. And so people just need to move into kind of a post-classical null hypothesis significance testing magic wand view of statistics. And this idea that if you take your data and you feed it through the wizard or the black box that is statistics, and if you turn the crank in just a certain way, you get the magic check mark of a p-value being less than 0.05, and therefore you've discovered a truth about the universe, and you can publish this and become famous. And that, unfortunately, even though they never admit it, is actually the underlying philosophy of a lot of scientists. They don't really understand statistics. And because of that, you know what we do when we're interacting with something we're forced to do, but we don't totally understand it, is you essentially bluster. You fake it till you make it, right? And so people fake it when it comes to statistics without truly understanding what the implications of what they're using are. And the end result is bad science. And if nothing else, if you want to be a scientist, you should have intellectual rigor to your work and some pride in your results. And unfortunately, if you just blindly use statistical models without understanding their fundamental assumptions, you're not doing science. You're cargo culting, and that's not a good thing for our society. It's not a good thing for science and its reputation. And it's not a good thing for science just as a whole, because, as I said, science is self-correcting, but it's a very slow process. And there's things that survive in the literature for decades before someone manages to disprove them because they were founded on bad science.
So in the perfect world, it would be like a number comes out and then two people argue, or a lot of people argue over whether this is good enough or not.
No, not at all. That again is a dichotomization. A number comes out. Fine. Publish it. It's a piece of evidence.
Okay.
That's it. Now do it again. Now do it again. Now do it again. And eventually come to a consensus about what an underlying physical law is. All of the really easy stuff is effectively done. You don't see a crisis of confidence or a significance issue in empirical chemistry. Because at the end of the day, if you describe a way to process a chemical using a certain reagent and a certain reaction in order to get another chemical out the other end, you publish the algorithm, and then Joe Smith at University Y goes, that's pretty cool, I wonder how that works, tries it, proves that it doesn't work, and immediately rebuts your paper with another paper that says Joe was a dumbass. And like chemistry is naturally self-correcting on a quick pace, because if you describe something that doesn't work, they fix it. Same with physics. You remember the faster than light suggestion? They knew it was wrong. The scientists who did it actively said in their archive paper, this is wrong. We know this can't be. But we can't figure out what we've done wrong. Like, we've triple checked everything. We've done all the observations multiple times. We've checked all of our instrumentation. We've had other people come in and run the instruments to make sure it wasn't us putting a bias in. We are at our wits' end. This thing still is implying a faster than light travel. So here it is.
Help us.
Shoot it down. Tell us what's going on, because we just can't figure it out. And within a few months, they figured it out. It wasn't anything they were doing that was dishonest. It was not an instrumentation error. It was a connection error. The way the logic was set up between the different pieces of computing was introducing a negative time lag that was actually, and once they corrected that, it went away completely, and they were getting speed of light. Exactly as they should. Self-correcting. Because if you found something that fundamental, either A, you made a mistake, or B, you're a crackpot. The speed of light seems to be a fundamental constant about the universe. So absent something like massive, massive gravitational pulls, you're not exceeding the speed of light, because it's all local reference frame. And so at the end of the day, they knew they'd done something silly, and so they fixed it. The problem is certain fields don't have that same culture, the culture of essentially combative collaboration, where everybody's in it together and we all want to discover the truth, but if you say something stupid, I'm going to shoot you down hard. And so you have some fields that don't have that, and so you get a lot of stuff published with very bad statistics, and no one ever calls them on it. And then you end up with a replication crisis. And it's kind of their own fault. It's not pleasant, but it's kind of their own fault. That's what happens if you use tools you don't understand. Eventually you get burned.
What's the difference between statistics and data science?
Depends who you ask. Depends what the day is. Depends what country you're in. At the end of the day, data science is a gussied up, prettied up version of statistics sold by computer scientists. Computer scientists are really good at selling things. They're really good at taking something that's been known for a while, giving it a new name, and making it the hypiest hype thing that it was ever hyped. Just look at deep learning. Heard of deep learning?
Nope. Sounds very cool, though.
Very hot, very cool. Deep learning is just neural nets. Neural nets have been around forever. Not forever, but, 25 years. They didn't work until they worked. And then they got a fancy name, and now they're going to change the world. And they're AI. It's like, they're not artificial intelligence. They're not an AGI. They're barely even a specific piece of artificial intelligence. They're just a model. They're nonlinear regression. And they're very black box. We have no idea how they work most of the time. You feed stuff in, you let it run for a while, and then it can actually tell you what picture that is. But they're very, very brittle methods. And so what is data science? Data science is what happens when people realize statistics is useful. But they don't want to do all the math, and they don't want to do all the underlying stuff. They don't want to worry about the assumptions. They just want to be able to turn the crank on data and get inference at the other side that they can use to sell stuff. So it becomes a hot area. And it coincided with the massive explosion we've had in data. So there, 20 years ago? Yeah, 99. Al Gore, currently at that time Vice President of the United States, did an interview, and he made a true statement. He said, there are more pieces of data in databases in the United States. 99% of that data has never touched a human neuron. No human's ever seen it. It didn't go through a human on the way to the database. It's entirely machine generated, machine saved, machine stored. And he was right. And the reason, you regularly see these reports of how much data humanity has created in all the epochs that humanity is known to have existed in. And we've created more data, more bits of information in the last 10 years than in the rest of humanity's history combined. Because we're recording everything, but we never see it. There's security cameras running 24/7 that are saving video footage that no one ever looks at. There's audio recorders running, saving audio that no one ever listens to. There are machines saving logs of events that no human has ever observed. So there's an explosion of data. And companies realize that actually the data that they are storing, some of it has value. And so that's why this is the digital gold rush. People are trying to dredge into their data to figure out what values they can squeak out. And so there's an explosion of looking for people who can look at that data and know what's going on. What they don't tell you is, unfortunately, 8 or 9 out of every 10 jobs in data science really should be a job in data engineering. It's all about storing the data and organizing the data and sorting the data, not actually doing the analysis itself, because most of a data scientist's job is just dealing with getting the data from one format to another in a way that they can actually even look at it. And I see that in my research. When I'm working on an applied problem with Health Canada or Environment Canada or one of the people I work with, they'll send me a whack load of data, and 80-90% of my time is spent massaging the data into a form that it's functional and ready for analysis, and then I'll spend a couple of days on the analysis and then I'm done. So what is data science? Data science is just statistics with a bit of computer science mixed in, and it is what statistics should be, at least I should say that. And this is on statisticians. We really dropped the ball. We're not very good at self-promotion. We're not very good at selling ourselves to the world. We've always, statistics has always been sort of quiet and off to the side. And when you look at what people are doing in data science, it's all just applied statistics. And a lot of the stuff that's being rediscovered is just statistical theory from the 50s and 60s. And it's sort of hilarious to watch them rediscover something that's, cutting edge. And I'm like, that wasn't even cutting edge when I was born. No less right now. It's like neural nets. They're not new. They were invented a while ago. The inventors of them just got an award. They're all still alive, but they're all pretty senior at this point.
Do you think statistics should be taught in high school to promote statistics?
Yes, and yes for another reason. So statistics should be taught in high school because it is a more fundamental set of skills that is more useful for a literate, numerate population than calculus. Calculus fundamentally is useless. It is a modeling language that is useful for a small subset of our population. The average person on the street does not need to know how to do a derivative or an integral or really anything to do with calculus. They don't even really need to understand functions. They do need to understand interest. They do need to understand taxes. They do need to have to understand how data works and what privacy means and what they should actually know about what companies are getting for them. There's an old saying that says, if you don't know how the company is making money, then you are the product.
Yeah.
Your data is the product. It's how they're making their money. And people aren't aware of that. And so we would be better off, and society evolves slowly, and so this is a problem, but we would be better off teaching students less math in high school and more statistics and probability, because at least those things would make them more numerate citizens. And then you can still teach math, but make it more of an elective thing. Right now we force students to go through, in the Ontario system anyway, English through to the end of their degree, math through close to the end of their degree, but science they can stop with year 10. And really, if you want to work in science, you don't. But maybe we should be doing that. Like maybe the required courses then on a high school sequence is year 9 and year 10 mathematics, year 11 probability, and year 12 statistics, and everyone has to take those. And then those who want to do mathematics or do physics or do chemistry also take their mathematics as the electives on top of that. But just in the same way that we have a required civics course, we should have a required statistics course. People should be aware of basic concepts of quantification of uncertainty. We use it in our everyday language. People talk about odds all the time. Yeah. They talk about chance all the time. We see it in newspaper articles where they write down confidence intervals for surveys that they've run for political viewpoints. How much better would our country be if all citizens who voted were also aware of how growth works and interest rates work and would understand that deficits aren't necessarily harmful? We might be better off. We'd have a more informed national discussion, which would lead to a healthier democracy.
Sounds about right. So I often wonder this for people who do programming for hobby, programs for fun. I don't know what they programs for fun, but I can kind of ask the same question in statistics. Well, I got this data points from this podcast that I'm doing. Is there any fun thing that I can do with these data points?
I don't know what data points you have, so I can't really answer that question. But there's all kinds of analytics you can run. You just have to have a question. Really, and that's the same with the programming. You just need an objective. You need something you want to answer. If you have an objective, a question you want to answer, yes, you can do statistics for fun to answer that question. And you can see how far your data goes. But if you don't have a question, then it's so much just intellectual curiosity, I guess. You can learn things just because you enjoy learning them, but you can do that for anything. You may be interested in quantum mechanics, not because you necessarily believe you're going to do a PhD in physics, but because it's kind of cool. So learn about it. And similarly, you can do the same with statistics, but really statistics, like computer science, like programming, shines when you have a problem you want to solve and you learn a technique and an algorithm and a methodology for solving that problem. And that's where you really get the reward.
So what are you working on now, research-wise?
I'm just wrapping up a 3-year project I've been working on with Health Canada on components of particulate matter and trying to build prediction models for estimating these components and then determining their impact on human health and the impact on our cardiorespiratory systems. I'm just wrapping up a project as well with Agriculture and Agri-Food Canada, where we're doing a sort of a feasibility study to determine what sort of models might be appropriate to run so we can try and model the impact of climate change and ozone changes on grapevine production in Canada, because it's a large export crop with a large GDP. And so we're interested in kind of how these things are going to affect the grape harvests in the future. And then also I have an NSERC grant, which is just a 5-year sort of discovery thing where it's independent research, and I'm working with a couple of graduate students on problems related to spectrum estimation, time series analysis, and imputation methods for the same. So those are the 3 projects I've been working on, although the last 4 months haven't made much progress because teaching sort of eats your life.
Wesley, thank you for joining me today. It was a pleasure talking to you. You can find the show notes of this episode on anchor.fm/naturally-curious. And until the next episode, stay curious.